Welcome to the class. Today we're going to have a look at the third lesson of chapter 7. Today's topics are electric potential and electric potential energy due to point charges. And we're also going to have a look at the Millikan oil drop experiment. So in the first section of this chapter, we have seen how a Van de Graaff generator in a science museum causes a hair of anyone in contact with the device to stand on end. At that point, the discussion dealt simply with the properties of electric charge and how the like charges, or electrons, on individual hairs caused the hairs to repel each other and spread out in all directions. We can look at this phenomenon in another way. The charge on the Van de Graaff generator creates a high electric potential on the conducting sphere of the generator. This potential provides an electric field that exerts a force on charged particles near the generator. This force, in turn, accelerates these particles. In fact, when the Van de Graaff generator was invented, it was an early type of particle accelerator. As a particle accelerator, however, the Van de Graaff generator has limitations. For one thing, it can only accelerate charges like those on the sphere. Although the potential on the sphere becomes too high with respect to the generator's surroundings, the air around the generator will ionize. This causes large sparks to jump between the sphere and objects at lower electric potentials, resulting in artificial lightning, which is shown here in figure 1. At a distance, the conducting sphere of a Van de Graaff generator resembles a point charge. In this section, we'll learn about electric potentials, electric potential energies, and electric potential differences for point charges and their surroundings. Okay, next, let's have a look at the concept of electric potential due to point charge. Earlier, we have learned about the electric properties of a point charge, right? This simple example is useful in many situations. In previous section, or section 7.4, we defined electric potential V in terms of a test charge Q and electric potential energy E subscript E or EE. The electric potential energy in turn depends on the position D of the test charge in an electric field epsilon. If the charge producing the electric field has the same sign as the test charge Q, the work done by the electric field on Q is negative. This means that delta EE is greater than 0 for delta D is greater than 0. And the sign of potential energy, and thus potential, is reversed from that of the uniform electric field. For a point charge Q, the magnitude of the electric field is given by epsilon equals KQ over R squared, right? We have already talked about this in previous sections. So setting the location in the field equal to the radius of the field, delta D equals R, the electric potential due to a point charge is inversely proportional to the distance from the charge and directly proportional to the amount of charge. So for point charge Q producing an electric field at the distance R from the charge, electric potential is then V equals KQ over R. Also, you could think of this using simple integration. So for example, if we choose 0 electric potential at infinite, distance from the charge Q. That is the reference point. Okay, just treat the infinite distance as a reference point. Then we know the electric potential at a distance from the charge Q is given by the integration of kq over x squared dx. When x is between r, is from r to positive infinity, right? So solve this equation gives us this expression is approximately equal to 0 minus kq over r, which can be simplified to kq over r. So that gives us the electric potential at the distance r from the point charge Q. Okay, just careful with this formula here. This is how we can calculate the electric potential of a point charge Q. So these results reinforce what we have learned about potential energy and the behavior of like and unlike charges. So suppose we put a source charge Q is greater than 0 at origin of the coordinate system in this figure, figure 2. The charge produces a potential given by kq over r, right? We have already proved this here. Then, if we place a positive test charge nearby, both the source and test charge are positive, so they repel one another, and the best charge experiences a force, and the test charge experiences a force that carries it downhill and away from the origin along the blue potential curve, as shown here in this figure. When the source charge is negative, the potential is described by the lower red curve in the same figure, as shown here. The source charge is now negative, so the attractive force carries a positive test charge along the red potential curve towards the origin. So note that conventionally, we choose the location whose distance is positive infinity from the source charge or Earth as the reference point where the electric potential equals 0, which is also called the reference point. So this is very similar to how we can calculate the gravitational potential, right? Usually we'll choose some point as a reference point where the gravitational potential is 0. So only changes in potential energy are important. So we must always be clear about choosing the reference point for potential energy. Electric potential is proportional to electric potential energy. So we must also pay attention to the reference point for electric potential. For example, when dealing with a point charge, follow the standard convention by choosing V equals 0 at an infinite distance from the source charge. All right. Infinite distance represents a distance so far away that any potential produced by a charge is negligible and for all intents and purposes equals to 0. In many other problems, we can also choose Earth as the reference point where the electric potential equals 0, because Earth conducts charge very well. Put another way, the electric ground is a point where the electric potential is 0. For 2 or more charges, use the superposition principle. Remember that electric potentials of negative charges are negative, and electric potentials of positive charges are positive. However, because electric potential is not a vector, the total electric potential of several point charges equals the algebraic sum of the electric potentials, resulting from each of the individual charges and their specific distances from the chosen location. Okay, just be careful that the electric potential is not a vector, but a scalar, okay? All right. Next, let's have a look at the electric potential energy of 2-point charges. So now consider the electric potential energy of a pair of charges. The electric potential energy of a pair of charges is the potential energy possessed by each charge in the pair because of its position. For a pair of charges, this potential energy is inversely proportional to the distance between the charges and directly proportional to the product of the two charges. For a pair of charges Q1 and Q2 separated by a distance r, we can use the equation for the electric field for the point charge Q2 and the definition of electric potential energy for the point charge Q1 in terms of V to determine the potential energy for the two charges. So first, we have EE equals Q1 times KQ2 over R, right? Then EE equals Q1 times KQ2 over R equals the electric potential of a pair of charges. Also, you can think of this as illustrated here in this lecture slide. You can choose zero electric potential at an infinity. From the charge Q, then the electric potential at the distance r from the charge Q is given by V equals KQ over R, right? We have just talked about that in the previous section, in the previous slide. Therefore, for a pair of charges Q1 and Q2 separated by distance r, the electric potential energy for the two charges is given by this formula. The electric potential energy EE equals Q2 times V1, which is Q2 times KQ1 over R, which is KQ1 Q2 over R. This is in accordance with our previous discussion, right? So this is qualitatively similar to the equation for Coulomb's law, except that EE varies as 1 over R, not 1 over R squared. If the charges are initially separated by distance RI, and then brought together to a final separation RF, then the change in the potential energy should be delta EE is EEF minus EEI, right? Therefore, delta EE is given by KQ1 Q2 over RF minus KQ1 Q2 over RI. Note that only changes in potential energy matter, right? And that EE approaches zero when the two charges are very far apart. The blue curve in figure 3 shows the general behavior of the electric potential energy for two like charges. In this case, EE is positive and increases as the charges are brought together. If the charges have opposite signs, the electric force is attractive or negative, and the potential energy is then also negative, as shown by the red curve in figure 3. Okay, so this is the basic concept of electric potential energy of 2-point charges. So I'll give you some time to have a look at the concept, and after that, I'll give you some examples to illustrate this concept. All right, next, let's consider this problem here. A point charge with a charge of 4.00 times 10 to the negative 8 coulombs is 4.00 meters due west from a second point charge with a charge of negative 1.00 times 10 to the power of negative 7 coulombs. A, calculate the total electric potential due to these charges at point P, 4 meters due north of the first charge. B, calculate the work required to bring a third point charge with a charge of 2.0 times 10 to the power of negative 9 coulombs from infinity to point P. Okay, I'll give you 5 minutes to consider this question, and we'll have a look at the solution together, okay? All right, let's have a look at the solution together. Okay, the total potential at P is the sum of the potentials due to the two individual charges, Q1 and Q2, right? And also note that the electric potentials are scalars, so we can use their arithmetic sum. We can use the equation V equals KQ over R to calculate the potential due to each charge, and use Pythagoras theorem to calculate the distance of point P from Q2, right? So distance between the distance of point P from Q2 is square root of R12 plus R1P, R1P square. So first of all, the electric potential due to Q1 is V1 equals KQ1 over R1P. This is 8.99 times 10 to the power of 1 Newton meter per coulomb. And then use the same method to calculate the potential V2 at point P due to Q2. And this gives us approximately negative 1.5892 times 10 to the power of 2 Newton meter per coulomb or joules per coulomb. Then we sum these two numbers up. This gives us the total electric potential at point P is approximately negative 69.0 joules per coulomb. As to the question B, we can use the definition of electric potential energy. The work done on Q3 is W equals Q3 times the electric potential at the infinity minus electric potential at the point P. So at infinity, the electric potential is 0, right? This is by convention. So W equals negative Q3 times VT. And this gives us the work done is approximately 1.4 times 10 to the power of negative 7 joules. Okay, any questions? All right, then let's consider another sample question here. A point charge Q1 with charge 2.0 times 10 to the power of negative 6 coulomb is initially at rest at a distance of 0.25 meters from a second charge Q2 with charge 8.0 times 10 to the power of negative 6 coulombs and a mass of 4.0 times 10 to the power of negative 9 kilograms, as shown here in figure 4. Both charges are positive. Charge Q1 remains fixed at origin, whereas Q2 travels to the right upon release. Can you determine the speed of charge Q2 when it reaches a distance of 0.50 meters from Q1? Okay, I'll give you 5 minutes to consider this question, and after that, have a look at the solution together. All right, let's have a look at the solution together. So there is no external forces applied to the system, right? So energy must be conserved. We can apply the law of conservation of energy using electric potential energy. The energy at the initial state should equal the energy of the final state. The charge Q1 remains fixed at all times. So the kinetic energy of charge Q2 and Q1 at the initial state is 0, right? And at the final state, there is kinetic energy for Q2 and also the electric potential energy of the system, right? So the difference of the electric potential energy between the initial state and final state should equal the gained kinetic energy of Q2, right? Okay, so follow this logic. We have the following relationship here. In the initial state, we have electric potential energy at initial state, noted by EI, plus the kinetic energy of the initial state, which is EKI, equals the electric potential energy of the final state, EEF, plus the kinetic energy of the final state, which is denoted by EKF. So use the formulas to substitute both sides. We have a simplified version for VF, which is a square root of KQ1, Q2 over MR1. Let's put all the values in. We have the VF final speed of Q2 equals 1.2 times 10 to the power 4 meters per second. So the statement is the speed of charge Q2 when it reaches a distance of 0.50 meters from charge Q1 is 1.2 times 10 to the power 4 meters per second. Any questions? Okay, then let's have a look at another problem. So this time we consider a head-on collision. Two particles, a proton with charge 1.60 times 10 to the power of -19 coulombs and mass 1.67 times 10 to the power of -27 kilograms, and alpha particle with charge 3.20 times 10 to the power of -19 coulombs and a mass of 6.64 times 10 to the power of -27 kilograms are separated by an extremely large distance. They approach each other along a straight line with initial speeds of 3.00 times 10 to the power of 6 meters per second each. Can you calculate the separation between the particles when they are closest to each other? Okay, I'll give you 5 minutes to consider this question, and after that, we'll have a look at the solution together. All right, let's have a look at the solution together. So in this case, we can use the conservation of energy to determine the separation of the charges at the moment when both particles have converted their kinetic energy into electric potential energy, right? So again, we have the following relationship. At the initial, at the initial state, the initial electric potential energy plus the initial kinetic energy should equal the final electric potential energy plus the final kinetic energy. At an extremely large distance, we know Ri should approach positive infinity, right? So the electric potential energy of the pair of charges will be zero. At minimum separation, the kinetic energy of the charges will be zero. So we know the initial electric potential energy should be zero. The final electric potential energy is KQ1, Q2 over RF. The initial kinetic energy is 1/2 times M1 VI1 square plus 1/2 times M2 VI2 square. And the final kinetic energy is zero, right? So substitute these expressions in the equation, we get the expression for the distance between the two particles in the final state, which is 2k q1 q2 over m1 vi1 square plus m2 vi2 square. And put all the values in, we can calculate the distance or the separation of the proton and the alpha particle is approximately 1.23 times 10 to the power of -14 meters. Okay, any questions? If no questions, again, let's revisit the Van de Graaff generator. The Van de Graaff generator discussed earlier produces an electric potential on the conducting sphere or dome by separating charge at one place and moving the charge to the conductor. As we can see here in figure 6, a moving cloth or rubber conveyor style belt receives electrons from a lower conducting cone at point A. The negatively charged part of the belt moves upward towards the conducting sphere and gives up the negative charge to the upper cone at point B. The charge travels to the conducting sphere and gives the dome a net negative charge. As the generator continues to run, the amount of charge on the sphere builds. When the charge reaches high enough levels, the electrons jump from the sphere through the air to another conductor brought close to the sphere, producing the artificial lightning seen here in figure 1. Okay, so that's the first half of our today's lesson. We can take a short break, and after that, we'll have a look at the second part of today's lesson, the Millikan oil drop experiment. All right, welcome back to our lesson. Next, let's have a look at the Millikan oil drop experiment. So physicists now know that each fundamental particle has a characteristic electric charge that does not change. In fact, the amount of charge is part of the definition of the kind of the particle. At the start of the 20th century, though, physicists still had many questions about the charge of fundamental particles. A big question was, is there a smallest unit of charge that nature will allow? And if so, what is the value of this charge? So in this section, we will read about a brilliant experiment aimed at answering this question that resulted in the first measurement of the charge of the electron. So physicist Robert Millikan set out in 1909 to examine the existence of fundamental charge using a series of experiments. Millikan's work demonstrated that the electron is a fundamental particle with unique charge. This electric charge is considered one of the few fundamental physical constants, measurable values that can be determined by demonstration and do not vary, that define nature laws. Millikan hypothesized that an elementary charge, which is denoted by letter E, the smallest unit of charge in nature, did exist, and that the charge of the electron equaled this elementary charge. To measure the charge, Millikan used a fine mist of oil droplets sprayed from an atomizer similar to what we might find on perfume bottles. The droplets picked up electric charges due to friction when sprayed from the atomizer. Millikan further hypothesized that the amount of charge any one drop picked up would be a whole number multiple of the fundamental charge. To measure the charge on a drop, Millikan used a device called an electrical microbalance. He allowed the oil drops to fall into a region between two oppositely charged parallel plates. The charges on the plates means that there is an electric field in the space between the plates, which creates a potential difference between the top plate and the bottom plate. Millikan connected the plates to a series of adjustable batteries so that he could adjust the magnitude of the electric field and therefore the electric force on the droplets. By adjusting the electric force to balance the downward gravitational force, Millikan could bring a charged drop of oil to rest in the region between the plates, which is shown here in figure 2. We can understand how Millikan used electric microbalance to determine the charge on an oil drop by comparing the electric and gravitational forces. For a drop of charge Q, the electric force from the field epsilon is given by the following formula: Fe equals Q epsilon. If we assume that the charge is positive, then we can charge the plates so that the electric field points upward and gives an upward force to the drop. We can then carefully adjust the potential difference so that the falling drop comes to rest between the plates. When this happens, the electric force balances the gravitational force. The magnitudes will be equal, which is denoted by this equation. Electric force equals gravitational force, Fe equals Fg, which means Q epsilon should equal mg, right? So in the previous section, section 7.4, we have learned that the electric field between two charged plates depends on the potential difference delta V, right? Which means epsilon equals delta V over delta D, where delta D is the plate separation distance. Therefore, we can solve for electric charge of the drop as Q equals mg over epsilon, which is mg delta D over delta B, right? Where delta VB is the special value of potential difference that balances the drop. So if we assume that we can measure the potential difference of our batteries and the plate separation, then we'll know the charge of the drop if we can measure the drop's mass. To measure the mass of a drop, Millikan simply switched off the electric field and observed the final speed of the drop at its fall onto the bottom plate. From the final speed, he could calculate the mass of the drop if he accounted for both the gravitational force and the force due to air friction. With this information, he could determine the charge on the drop. Millikan repeated his experiment many times, balancing a drop, measuring the voltage, letting the drop fall, and measuring its final speed. When he analyzed the data, he discovered that the hypothesized pattern, the values of the charges he measured were whole number multiples of some smallest value. And no drops had less charge than this value. Millikan concluded that this charge value equaled the elementary charge of the electron. In fact, we now think of this positive number as the charge of the proton, but the absolute value is the same for electrons. Later experiments by other researchers confirmed Millikan's results and improved the accuracy of his findings. The current accepted value of the elementary charge E to 4 significant digits is given by E equals 1.602 times 10 to the power of -19 coulombs. With this value, we can connect the charge of an object and the difference in the number of electrons versus protons in the object. If an object has n more protons than electrons, it has a charge Q given by Q equals NE. Okay, just put this important constant onto your notebook or use this to solve questions in this chapter. Okay, next let's have a look at a sample problem. Calculating the charge on object. Can you calculate the charge on a small sphere with an axis of 3.2 times 10 to the power of 14 electrons? Pretty straightforward question, right? I'll give you 2 minutes to solve this. All right, have we finished? Okay, let's have a look at the result. Okay, because we have Q equals NE, right? Where E equals -1.602 times 10 to the power of -19 coulombs, because we have an axis of 3.2 times 10 to the power of 14 electrons. So the charge on sphere should be negative, right? Therefore, the total charge on the sphere is given by 3.2 times 10 to the power of 14 times negative 1.602 times 10 to the power of negative 19 coulombs, which is approximately negative 5.1 times 10 to the negative 5 coulombs. Any questions? Okay, then let's consider another problem. So in a Millikan type experiment, two horizontal plates maintained at a potential difference of 360 volts are separated by 2.5 centimeters. A latex sphere with a mass of 1.41 times 10 to the power of negative 15 kilograms hangs between the plates, the upper plate of which is positive. There are three questions you need to answer. First, is the sphere negatively or positively charged? Second, can you calculate the magnitude of the charge on the latex sphere? Then determine the number of excess or deficit particles on the sphere. All right, I'll give you 10 minutes to consider the question, and after that, we'll have a look at the solution together. Okay, you can start now. All right, let's have a look at the solution here. Okay, in question A, the electric field lines run from positive charges to negative charges. So the field between the place point downward. We know that protons will move in the same direction as an electric field, and that electrons will move in opposite direction to the electric field. The electric force on the sphere must point upward to balance the gravitational force, right? So the sphere's charge must be negative. In question B, we know when the sphere is balanced, the electric force balances the gravitational force. So we can use the equation for solving for electric charge of the oil drop using the Millikan experiment, where Q equals mg delta D over delta VV. Also note that 1 volt should equal 1 Newton meter per coulomb, and 1 Newton is also 1 kilogram meter per square second. So solve this equation gives us Q is approximately 9.596 times 10 to the power of negative 19 coulombs. So the actual charge is negative, since this value gives the magnitude of the charge. Okay, so in this third question, we know the total charge is, the magnitude of the total charge is 9.596 times 10 to the power of negative 19, right? So use the equation that connects the charge of an object with the number of excess protons in the product gives us Q equals NE. Therefore, N should be 6. Since the sphere has a negative charge, we know the excess charges must be electrons, right? Therefore, we know there are 6 excess electrons on the sphere. All right, any questions? Okay, last but not least, let's have a look at the charge of a proton. The elementary charge is the electric charge of a proton, which is equal in magnitude to the absolute value of the electric charge of the electron. Careful experimentation has constantly shown that the two particles have charges that are equal in magnitude. This result is actually a surprise, because the electron and proton have very little else in common, including their masses and their roles they play in the structure of a matter. Furthermore, physicists think of the electron as a fundamental particle with no inner workings, but they now view the proton as a combination of more fundamental particles called quarks. The proton consists of 3 quarks, all of which have charges that are either exactly 1/3 or 2/3 of the elementary charge, despite having fractional charges. So no experiment has detected any combination of quarks in nature that have a total charge whose magnitude is less than E. For this reason, physicists still refer to E as elementary charge. In fact, every subatomic particle that researchers have so far detected has a charge whose magnitude is equal to a whole number multiple of E. Researchers also believe that the amount of charge in an isolated system is conserved like energy. Unlike energy, electric charge does not come in different types and cannot change from one form to another. No interaction can destroy or create electric charge, and the total electric charge of the universe remains constant. Okay, so this is the end of today's lesson. I'll see you next time. Bye.